Record, please. Okay, so remember this Desmos activity from yesterday?
Mm-hmm.
You were kind of investigating on your own what the graph of a derivative might look like for a variety of different functions, and then trying on your own to sketch what the derivative would look like for a couple of given different functions. What was important about the derivative at these 2 points?
So the graph like changed direction.
So from increasing to decreasing, or from decreasing to increasing, the graph changes direction. So I know that this is the maximum and minimum. The slope of the graph at those maximum minimum points would be what? 0. The derivative is 0 at any maximum or minimum, because isn't that like where the graph is really flat as it's changing direction from increasing to decreasing and vice versa? What's the value of the derivative? What's the sign of the derivative when the graph is increasing? So on the left and the right, what sign would the derivative have? Positive, because wouldn't the tangent line be going up? How about when it's decreasing in the middle between those 2 relative maximum points? Negative. So if I move the slider here, it's going to plot the derivative. And like we mentioned, at -1 and 3, the derivative is equal to 0, because that's where the graph is the flattest, where it changes direction, where it has its relative maximum and minimum. The derivative is positive, so these points are above the x-axis where the function's increasing. As the graph is really steep, the derivative is further from 0, because it's the steeper part of the graph. The slope of the tangent line would be the largest of the steeper parts of the graph. Where the curve starts to flatten out, like right here, now the derivative is getting closer and closer and closer to 0, because the slope is becoming less and less and less for the slope of the tangent. Where the function is decreasing, where it's going down from left to right, now the derivative would be negative, because the tangent line would have a negative slope. On the slides here in a minute, we're going to talk about what happens to the derivative at a couple of corner points. These are corner points. The graph is changing direction abruptly or suddenly. So the derivative is going to go from a very negative value to a very positive value very quickly. It changes abruptly all of a sudden. So when I graph the derivative, it's going to have a really big jump at -4 and 0. This is called a corner point or a cusp. The direction of the graph changes very suddenly. It goes from really decreasing, really negative slope to increasing, really positive slope, which is why I go from this point on the derivative here to all of a sudden up here. The derivative would not be a smooth curve in this case. All right. Here's one where you had to sketch your own derivative. What would the slope of, I've got kind of 3 different pieces here. What would the slope of this line be? It's a straight line, so what's the slope of a horizontal line? 0. The derivative would always be 0 for any point on this line, because for any point, isn't the slope of the graph always 0? What's the slope of this line? -2. And isn't the slope always -2 for any point on the graph? So no matter what, any point I pick on this line, the slope is always going to be -2. The derivative is always going to be -2. That's why it's a line. It has a constant slope. In the middle, now the slope is no longer a constant. I'm starting with a very negative slope. It's getting flatter and flatter and flatter till it hits the minimum on the bottom. And it starts to increase and go up from there. The derivative is getting larger. The graph is increasing in the curve from left to right. So I look at what that's going to be. Here's a graph of the derivative. For the horizontal line on the left, the derivative is 0. For the negative slope line on the right, the derivative was -2 for any point on the curve. And here in the middle, the derivative starts to be really negative, and as the graph's flattening out, the derivative is getting closer to 0, and eventually the derivative becomes positive as the graph starts to increase. Does that sound okay from what we did yesterday? All right, then let's get into a couple slides here. I have a couple of pieces of information when it comes to the properties of the derivative and its graph for here for statement 6. A lot of things we just talked about, and hopefully you investigated on your own from that Desmos activity from yesterday. When a function is increasing, the derivative must be positive. When a function is decreasing, the tangent line would be pointing down, so therefore the derivative would be negative. The steeper the graph, the larger the derivative, because the slope of the tangent line would be greater. The flatter the graph, the closer the derivative is to 0, because the slope of the tangent line would not be quite as extreme. At any point where the original function has a relative maximum or minimum, we know that the derivative must be equal to 0. That's where the flattest curve, that's where the flattest part of the curve is at. That's where it changes direction, increasing to decreasing or vice versa. So the derivative has to be 0 at any point where there's a maximum or minimum on the function. Hopefully nothing too earth-shattering there from what we did in class yesterday. Should make sense. As you can kind of see on this graph here, I have a function plotted in red. The tangent line is a positive slope where the function is increasing, so therefore the derivative is greater than 0. At the maximum point on top, I know the curve is at its flattest point, so therefore the derivative has to be equal to 0. Where it's decreasing, the tangent line is pointing down, so the derivative is negative. How about this point right here? What's important about this point? At B, what's happening to the graph? Changes direction really fast. It's got a corner point or a cusp. Sometimes this is called a cusp, C-U-S-P, a corner point. The direction of the graph changes abruptly. Like it goes from really decreasing and then all of a sudden really increasing. So the derivative isn't going to be a smooth curve at x equals b. It's going to change sign really abruptly from really negative to really positive. In that case, the derivative at b is what's called undefined. In these next couple of slides, I'm going to talk about a few different ways where the derivative might be undefined. One of those ways is if there's a corner point in the graph, otherwise called a cusp. The derivative or slope of the graph changes dramatically at a corner point, so therefore the derivative is undefined. It changes abruptly. The derivative can't take on every value between that negative number and that positive number, so therefore the derivative is undefined. All right. Next slide here talks about non-differentiability of a function. Differentiability means the function has a derivative at that point. I'm able to find the value of the derivative at that point. I'm able to take the derivative of a function and evaluate it at that point. So non-differentiability means that I can't do those things. I can't find the derivative at that point. The slope of the line, the slope of the tangent line has no value at that point. There are 3 reasons why a limit would fail to exist. There are 3 reasons why the derivative would fail to exist. The derivative of a function, the slope of a graph of a function, does not exist at x equals a when either of these 3 things are true. The function has no slope has no derivative when the graph has a corner point or a cusp, kind of like this part right here. At x equals b, there's a corner point. The derivative or the slope of the graph changes so dramatically that we can't define the derivative at that point. If I go back to your Desmos activity from yesterday, that's pretty much what this is saying right here. At those corner points on -4 and 0, the derivative changes so dramatically that we really can't define the derivative at that point. It's not a smooth curve at that point, so the derivative does not exist. Next, I know there is non-differentiability when the function is discontinuous at x equal a. How can the function have a tangent line at a point when there is no point on the graph? If it's not continuous there, then how can I put a tangent line there? So if it's discontinuous at x equals a, it's not differentiable. There is no slope of the graph at that point. Lastly, if there's a vertical tangent line at x equals a, if the tangent line to the graph is vertical or straight up and down, it's not differentiable. Now, why would that be? What's the slope of a vertical line? If the tangent line is vertical, what's the slope of a vertical line? Undefined. So if the tangent line is vertical, the slope of the graph is undefined because it wouldn't make sense for us to have a slope there. It's so extreme, it's so steep that we can't have a slope there. It's infinity. The slope of the graph is infinite. It's not a real number. It's undefined. Okay. Here's kind of three pictures that will go with those three reasons. If it has a corner point or cusp, CUSP, the slope of the graph changes from really positive to all of a sudden really negative. So it's not a smooth curve. The derivative is undefined at this corner point, x equal a. If it's continuous, if it's discontinuous, pardon me, there is no slope of the graph. Where's the tangent line? If there's a break in the graph, if there's no point on the graph. If it's discontinuous, the graph has no derivative or no slope of the function at that point. Okay. Lastly, the vertical tangent line. On this third picture for part C, at point x equal a, the graph is so steep that the tangent line becomes vertical. It's decreasing so much that the slope of the graph is pretty much straight up and down. No slope of a vertical line. The vertical line is undefined, so there is no slope of the graph at that point. It's not a real value. Questions there? Three reasons why a graph is not differentiable. Has no derivative. Corner point, discontinuous, or vertical tangent line. Would look something similar to those three images. There is a key point here to make when it comes to differentiability and continuity. Differentiability means there's a slope of the graph at that point. What does continuous mean? The function's continuous, then it's defined. The limits as x approaches that point is the same from the left and the right. There's no hole there or skip there or disjoint broken graph there. So how does differentiability and continuity affect each other? How do they kind of work together? So here is a true statement. If a function is differentiable at some point, then it is also continuous at that point. Differentiability implies continuity. If a function is differentiable there, then it's continuous there. If I can find the slope of the graph there, it has to be continuous there. However, the reverse of that statement is not true. If I flip that around and find its converse, continuity does not imply differentiability. Just because it's continuous there does not mean that it's always differentiable there. If a function is continuous, it may not necessarily be differentiable at x equal a. Why would that be correct? How can something be continuous but not differential?
You can have a vertical
Tangent line or a cusp, those reasons that are posted right there. Look back at this picture. On these two images on the left and the right, the function is continuous at a. Is it differentiable at those 2 points?
No.
Just because it's continuous does not mean it's differentiable. However, if it is differentiable, I do also know it's continuous at that point. All right, so let's practice this. I think I got a few different examples here. We're going to describe the differentiability of various different functions. Describe the differentiability of f of x equals the absolute value of x minus 3, and I also have the graph to the right. So just like we described continuity with different intervals, and we just said if it's discontinuous at a certain point, we gave a reason why, let's do the same thing for differentiability. On what intervals is this function differentiable? Or in other words, where is it not differentiable? Let's answer that. Why is it not differentiable at x equals 3, Caitlin? Because there's a corner point. The derivative changes from -1 to all of a sudden +1 at x equals 3. So not differentiable at x equals 3 because the derivative or slope of the graph changes so dramatically. It's abrupt change in the derivative. So for number 1, my function is differentiable on the interval -∞ to 3 and 3 to infinity. It's not differentiable at x equals 3 because 3 is not a part of either of those two intervals. The reason being it's not differentiable is what again? There's a corner, there's a cusp. I always like saying that word, cusp. C-U-S-P at x equals 3. Just like we described intervals where a graph is continuous, we could do the same thing for where it's differentiable. If it's not differentiable at any point, tell the reason why. It could be a cusp, a discontinuity, or a vertical tangent line. Here's a graph of the cube root of x, the third root of x. Where is this graph not differentiable? Why is it not differentiable at 0? Vertical tangent line. If I were to graph the tangent line, let me kind of grab my yardstick here and we'll look at it. If I was to kind of plot the slope of the graph, what's the slope of the graph on either end, at the far left and right? The slope of the graph is pretty close to 0 because isn't it pretty flat right there? The tangent line would be pretty flat on the far ends of the graph. But as I move to the left and right here, what's going to happen if they get closer and closer to 0? Now all of a sudden, this tangent line is starting to go straight up and down, is it not?
Yeah.
At x equals 0, isn't the graph basically just a vertical line? What's the slope of a vertical line? Well, that's undefined. It's too steep to have a slope. So question 2, the cube root of x is differentiable on the interval -∞ to 0 and 0 to +∞. Why is it not differentiable at x equals 0? Or the finish line. Take a minute for that last slide. I think there's one more. Yep. This is 1 over x plus 2 squared. So for 3, your function is f of x equals 1 divided by quantity x plus 2 squared. Describe the differentiability. Where is the graph differentiable? And if it is non-differentiable anywhere, explain why not.
Briley Applegate, report to the secondary office. Briley Applegate, please report to the secondary office.
Where is it not differentiable?
-2.
At -2. So let's write those intervals. Differentiable on the interval -infinity to -2 and -2 to infinity. We know it's not differentiable at -2 for what reason? It's discontinuous. There's no point in the graph at -2 because it's undefined for x equals -2. So it's discontinuous at x equals -2. Just because a graph is continuous doesn't always necessarily mean it's differentiable. Those first two slides, the function's always continuous for any real number, but it's not differentiable for certain values. Like on number 1, it's continuous at 3, but it's not differentiable there. It's continuous at 0 here on graph number 2, but it's not differentiable there. Continuity does not imply differentiability, but differentiability does also imply continuity. If it's differentiable there, then I also know it's continuous. All right. Anything else, guys? Cool. I think we'll do some more practice with sketching our own graphs of the derivative next week. See if we can't get this one to be wrapped up later towards the end of the week, like on Wednesday or Thursday. With another quiz on fans. Otherwise, have a great weekend.
Thank you.